So what is radioactivity and what types of radioactivity do we categorize? While Curie focused her work on discovering the kinds of radioactive elements, and Ernest Rutherford, we've heard his name before in the evolution of atomic theory. He is the person given credit for discovering the nucleus, this very dense, very heavy region of an atom where protons and neutrons are found. So Ernest Rutherford was focusing on characterizing radioactivity itself. So Curie and Rutherford were scientists that were finding emissions being produced by the nuclei of radioactive atoms. Such nuclei are very unstable, spontaneously decompose, and they emit small pieces of themselves to gain stability. And we notice the larger and larger and larger an atom becomes, the more unstable the nucleus becomes. We also realize that the number of protons in the nucleus, if it indeed matches the number of neutrons, if they are indeed the same number, that creates the most stable arrangement. So when we start seeing atoms that have large number of neutrons compared to the number of protons, we can start to detect instability inside of that nucleus. So if nuclei are unstable, they will spontaneously decompose and emit small pieces of themselves to gain a more stable arrangement. And it's these fragments that are radioactive. So it's this radioactivity that Becquerel and Curie detected, and natural radioactivity can actually be categorized into 3 different areas. We'll talk about 5 types of radioactivity, but looking at types categorized and we'll talk about alpha, beta, and gamma radiation. So thinking about categorizing types of radioactivity into alpha decay, beta decay, and gamma ray emission. We will also look at positron emission and a process known as electron capture. So each of those will be discussed one at a time. Alrighty, hoping that the slide catches up here in the presentation. Alpha decay, beta decay, and gamma ray emission are the types of radioactivity. In order to understand these types of radioactivity, we must briefly review some notation or symbolizing of isotopic structure. If we discover the 3 types, alpha, notice the Greek symbol, beta, also a Greek symbol, and gamma rays, which is not a particle at all, but only a type of energy. We can see it also has a Greek symbol. And in addition, we will look at positron emission. That might be a brand new word for us, positrons. Again, if an electron is a massless particle carrying a negative charge, positrons are actually a massless particle carrying a positive charge. Friends, in the nucleus of an atom, there's just so much more to it than saying there's only protons and neutrons, because them themselves are built up of smaller particles, and then those smaller particles are built up of even tinier things. We start introducing terms in the nucleus that we may have never heard of before. So alpha rays have a charge of a positive 2, and that Cu stands for Coulomb unit, and a mass of 4 AMU, atomic mass units. We now know that to be a helium nuclei. Beta rays have a charge of -1 Coulomb units and have a negligible mass. Well, that meets the criteria as a description of an electron. Now, I know electrons have a mass, but compared to the weight of the nuclei particles, it is so small, so negligible, and we just disregard it and call it massless. And gamma rays form of light energy, not a particle like an alpha or a beta particle, but simple straight out energy waves. So in addition to these 3 categories of radioactivity Rutherford discovered, we do have some unstable nuclei emitting positrons, which are positively charged particles like an electron would be negatively charged. And then some unstable nuclei will undergo electron capture, which really draws an electron into the atom itself to help create a lower electron energy arrangement, pulling it right into the nucleus. With Rutherford's experiment, if you take a look at its slide, you see that Rutherford's experiment uses something called a cathode ray tube. And what that shows us, we have a particle, such as a uranium crystal, if you will, emitting certain radiation, and what he's trying to do really is detect with electromagnetic waves how we can manipulate and separate out the three different categories of alpha, beta, gamma. So if this is a source of electromagnetic radiation here to the left of that slide, it's going through an opening in a cathode ray tube, and as he separates out based on charge, notice on the top there's a positive field, and on the bottom there's a negative field, and straight across is no attraction at all. So what this slide is showing us is that there are three different categories of radiation. One source, if I look at the top with the beta sign, if a beta is attracted to the positive field, in and of itself must be negative. Beta, if you recall, matches the criteria of an electron. Well, it makes sense. Electrons are negative. That would be drawn towards the positive field. Down below, notice here where an alpha particle is being attracted to in the negative region. So if alpha particles, which meet the criteria for a helium nuclei, which is positive protons and neutral neutrons, two of each, if that's being attracted to the negative field, alpha particles must indeed be positive themselves. And if gammas go straight through, they are non-charged, a simple radiation coming out in a form of energy, not a particle at all, so it's not attracted to an electrical field, therefore it must be no charge. In the next slide, you see the penetrating ability of radioactive rays. And again, we have a source of an electromagnetic field, and what we're noticing is the penetration ability based on the thickness of the lead shield. If you've ever gone in and had an X-ray, perhaps either as a body part or as part of a dental examination, they'll take x-rays of your teeth. You'll notice that the technician will either completely step out of the room or will put a shield over you if you are sitting in the dentist chair and getting a tooth x-ray. They will shield you with a lead apron. Alpha rays are blocked at a small thickness, very tiny, 0.01 millimeter will block an alpha ray. They are larger particles, 2 protons, 2 neutrons as a helium nuclei. Beta go through that small thickness there and will, however, be stopped with a 1 millimeter piece of lead. Beta itself can be blocked with a piece of lead, but notice this massless energy wave of a gamma goes straight through no matter how thick the piece of lead. So 100 millimeters thick, 100 times the thickness of a beta, and it's still going right through. So we can see that the energy involved in a gamma ray is much, much higher and can just go straight through a lead blockage. So let's take a further look at each of these categories and think about facts of the nucleus. I have to let this catch up a moment. When we think about the nucleus and what is inside, we have protons, which we know are positive. We have neutrons, which we know are neutral, and there is this force that actually keeps this entire nucleus together. It actually has the name of a nuclear force. It was discussed, I believe, in physical science class. We know that the volume compared to the entire size of the atom is very, very small. That inside of the atom is mostly empty space. This electron cloud is a vast volume. But the nucleus is essentially the entire mass of an atom. So it's a very small, very heavy, very dense area composed of protons and neutrons being held very tightly together. Again, that is a field of force known as the nuclear force. And the particles that make up the nucleus we know are protons and neutrons, but if we wanted one word to mean either of them, we call those nucleons. So inside of the nucleus, we know that it's very heavy but very small. So thinking about what is inside, we think about protons, we think about neutrons, and we have symbols that represent each of those. So inside of the nucleus, we have protons and neutrons, and we represent that information with something called a mass number and an atomic number. And when placed next to the chemical symbol, we come up with what's called a standard notation. So every atom of an element has the same number of protons. Remember, the proton number gives the atom its identity. So if I said number 1, you know it was hydrogen. Number 2 would be helium. Number 3 would be lithium. That very number, called the atomic number, tells us the protons, gives the atom its identity. However, atoms of the same element can differ by the number of neutrons inside of that nucleus, and that term is called isotopes. The isotopes, remember, add different varying combinations of neutrons to the same number of protons. Therefore, we know isotopes are going to weigh different. If the sum of protons and neutrons give us the atomic mass, or mass number if it's a whole number integer, that's called A, the mass number, and that's just simply found by adding protons and neutrons together. So facts about the nucleus would say that any isotope consisting of protons and neutrons can differ by the number of neutrons, but they must have the same number of protons. An isotope specific to that element is called a nuclide, N-U-C-L-I-D-E. Now look at this stat. Less than 10% of the known nuclides are non-radioactive. That's very surprising. We could flip that to a more alarming statistic. 90% of all nuclides emit radiation. We can identify any nuclide with its isotopic symbol element, including the mass number and the atomic number. So for any element X, we place the mass number on top, the larger of the two, and the atomic number on the bottom. Radioactive nuclei spontaneously decompose into smaller nuclei, and that's what's known as decay. And remember that the more stable the arrangement, the slower this process occurs. Some elements, of course, decompose within fractions of a second. Some take thousands and thousands of years to undergo decay. However, they would be considered spontaneous. The word spontaneous doesn't give us any inclination of how long the process takes, just the fact that it is occurring. So radioactive decay is spontaneous as they decompose into smaller nuclei. And because that nuclei are unstable, they're trying to create a more stable arrangement by emitting particles. A light energy perhaps, an actual particle such as alpha or beta, but they're trying to arrange themselves to be creating a positive to nucleon arrangement that meets the criteria of stability. The parent nuclide is the one that is unstable, and it gives off what's called a daughter nuclide, the more stable arrangement. And again, when we say spontaneous, it doesn't give an indication of how long it takes, but just that it is occurring. Take a moment of time and look at these important atomic symbols. The proton, we know, consists of a positive charge. Its symbol in chemistry has been P positive. However, take a look at its nuclear symbol. If a positive proton can be represented by a hydrogen atom, that makes sense. If the hydrogen is number 1 and its mass number is 1, 1 minus 1 is 0. Hydrogen has 0 neutrons as its most abundant form of an isotope. So a nuclear symbol for a proton would represent the hydrogen atom. The neutron, of course, weighs 1 and has a neutral charge of 0. So its nuclear symbol places its weight on top of 1 and a 0 charge on the bottom. Proton can be represented that way as well. Notice it has a mass of 1 and a charge of a positive 1. So P1 over 1 is representing the mass number on top and the charge that it's carrying down below. Compare that to the electron, which is massless. So we represent the weight of an electron as 0 and its charge is negative 1. An alpha particle, notice the Greek symbol for the alpha sign, is a helium nuclei. Alpha 4 over 2. 4 indicates 4 particles in the nucleus, 2 of which are protons, 2 of which are neutrons. The beta, we said, represented meets the criteria of an electron. So as an electron, we see that they are 0 over negative 1. And a positron would represent 0 over a positive 1. Positrons and electrons are opposite charges, and they are both massless. Alrighty. So what we're doing is reviewing some standard notation in the middle column versus a nuclear symbol in the far column, and just trying to identify in a next step how we can begin recognizing similarities between symbols we're more familiar with and the nuclear symbol being represented. Let's say, for example, we have a symbol of neon, 21/10, that would represent a neon isotope that contains 10 protons and 11 neutrons. The symbol neon 20/10 would represent the neon isotope that contains 10 protons and 10 neutrons. Excuse me. Remember that Remember that most elements that have different number of isotopes, and when discussing nuclear properties, we often refer to that particular isotope as a nuclide. Thinking about main subatomic particles as protons, neutrons, and electrons, we're very familiar with standard notation of proton, neutron, electron, protons being positive, neutrons are neutral, electrons are negative. The 1 in the lower left of the proton represents 1 proton, and 0 in the lower left of the corner of the neutron symbol represents 0 charge. The negative 1, of course, represents it's a negative number, negative charge. So alpha decay, beta decay, and gamma emission. Alpha, beta, and gamma, those three that we'll be focusing on. I'm going to pause here in the video and let the slides catch up, and we'll take a closer look at each of those three considerations.